Okej. Atëherë, faleminderit të gjithëve që jeni bashkuar sot në eventin e 5 të Albanian Role Models in Technology. Ju falenderoj për pjesëmarrjen. Eventi, qëllimi i këtij eventi është jo vetëm të promovojmë femra dhe gratë, goca dhe vajzat të cilat kanë një sukses në fushën e teknologjisë, por gjithashtu t'japim edhe një shembull të mirë se si mund t'ja dilet banë. Sot jemi të nderuar që na është bashkuar me ne Flutra Osmani. Ajo është një software engineer, nuk është e zakonshme që një gocë të jetë një software engineer. Ajo do na tregoj udhëtimin e saj, rrugtimin e saj se si e ka dalë banë, ndërkohë që do mbaj edhe një talking, technical talk, për sa i përket një fushë të caktuar. Kështu që po ja lë më shumë fjalën Fluturës dhe e ndjekim. Faleminderit.
Punoj në një startup këtu në Silicon Valley që quhet Earnin dhe produkti që në të cilin ne punojmë mundson marrjen e një pjese të rrogës para se ti të paguash nga punëdhënësi. Domethënë është startup në domenin e fintech, si quhet këtu. Para kësaj kam punuar si software engineer në Netflix dhe aty kam punuar në një ekip që ka ndërtuar këtë infrastrukturën për atë që quhet encoding pipeline. Kryesisht jeta ime ka kalu në akademi një kohë të gjatë, pak në Zvicër dhe pak në Suedi e Finland. Dhe ka disa tema që më kanë interesu gjatë rrugtimit akademik. Në fillim siguria, security, dhe kam marrë shumë klasë të cilat kanë qenë të lidhura me kriptografi dhe këto protokollet e sigurisë. Po pastaj pas një kohe jam përfshirë në disa projekte kështu research projects që kanë të bëjnë me distributed systems dhe mendoj se është temë shumë e madhe, është thjesht disiplinë në vete dhe edhe tash pas shumë viteve mendoj se ka shumë aspekte të cilat dhe vetë është vështirë t'i kuptoj, po me përvojë pune kam arrit t'i kuptoj disa aspekte të cilat është vështirë t'i bresh vetëm kur i studion nga aspekti teorik. Sot do të mundohem ta paraqes një përmbledhje të fushës edhe ta ilustroj me disa shembuj pak më konkret. Mund të flasim edhe pas prezantimit nëse keni pyetje edhe për se si me qenë se është një organizim që mund do t'i inkurajoj femrat të futen në teknologji, që t'rregoj një 2-3 fjalë se si duhet pas motivim edhe inspirim për të studiu në këto fushat e teknologjisë. Nuk është ndonjë fushë e pakapshme për ne. Ne shpesh përballemi me shumë dilema apo me shumë dyshime të cilat na zmbrapsin, edhe kryesisht psikologjike, jo barriera kështu konkrete që mund të na ndalin të studiojmë çka që kemi dëshirë. Po filloj një me temën e pastaj mund të flasim edhe të diskutojmë nëse keni pyetje tjera. Se do ta ndaj ekranin me ju. Okay. Besoj se po shihni ekranin.
Është në rregull.
So, I'm going to focus on a topic that is that we see everywhere in practice, and that is a common topic among many companies, whenever they are building their services that are reliable and scalable to millions of users, they inevitably have to work on systems that are so-called distributed systems. I'll focus a little bit on what they are, why different companies build them, and how to build them. I'll try to provide a little bit of an overview, but mostly illustrated with some practical examples. If we just look at its definition, a distributed system is a system where its various components are located in different networked computers. So both the program and the state may be divided in various computers. These computers, as I said, are networked and they talk to each other over typically message passing. One such technique is called RPC, remote procedure calls, but there are other alternatives like they can use message queues to pass messages between each other. So what do I mean by this? What does it mean to divide both state and the program into different networked computers? So you can, for example, work on something like a document in your computer and then save that document that you worked on. So far, so good. This is straightforward. However, if your laptop crashes for some reason, then, or the hard disk is corrupted, then your document that was stored locally is lost forever and you cannot access it elsewhere, because both the program and the state that you generated, the document itself, are stored or located in the same machine. Therefore, the state that you basically generated by writing this document is lost. So think of another example now, a typical Google Doc, where you would be writing this document and a copy of this document is stored somewhere in the cloud, provided by, in this case, Google. If your personal computer crashes, you would still be able to access this document that you wrote in some other computer. So basically, the state, the document itself, the resource itself, is stored somewhere else. Even in that cloud, if one of the servers that is storing the copy of your document fails, then there are other servers that hold the same copy, and they are called replicas. So we see just a basic example of a distributed system in practice. Basically, serving you, providing you a service that in itself consists of various components that are spread across different networked computers that talk to each other. So typically, in a centralized system, you have one server, like the red dot right here, that is serving various consumers. And there are many things that can go wrong in this model. First of all, there are so many users that you can serve. At one point, you hit the limit and you cannot serve more users than a particular number because it's just one server serving them. And then it can be a single point of failure. If this server fails, it loses both the state for all these users and the service itself. So it is a single point of failure. If we look at the right-hand side, this is one example of a distributed system where for each of the services you have, for each of the servers, which is this, this bigger dot, is you have backup servers. If any of these servers fails to serve you, there will be backup servers to come up. This is one form of a distributed system, but it's not an extreme example like it's, for example, a peer-to-peer system. in a peer-to-peer system, this model looks slightly different, where you don't have a concept of a server and users or clients, but each node or each computer in the network serves both as a client and as a server, and they share both the computation load and resources as all other nodes. So basically they are equivalent. So most of this talk is focused on this distributed system example that I have outlined here, where somehow which is to some degree it's decentralized, and we're talking about server resources being offering the service, and then if they fail, having redundancy built in. So what are some other practical examples that we can see today, just to better understand the point of this or their significance in today's world? One such example is DNS, domain name system. It's widely used across the internet. Every time you go to a web browser and you type google.com, basically you're translating that host name to an IP address using DNS. And DNS is just a lookup table of host names like google.com to IP addresses. And there are many of these lookup tables distributed across the globe, and they are serving various users across the globe. So one user in US and one in Japan is probably looking at different DNS lookup tables that are closer to them to resolve these names. And of course, they also have backups. If one of them fails, there are backup lookup tables. Another example is email. Sure, you can have a personal email, or you can be a very small company with a small number of users. This might even be a centralized system if you wish. But larger email services like Gmail that have a lot of users are distributed. They are powered by the underlying SMTP servers, the mail servers that are relaying your email from you as the source to the destination. And of course, there is redundancy and fault tolerance built in these email servers. If one of them fails, there will be another one that will be relaying your email to the destination. Different big companies, for example, like Facebook and Google in the recent years or the past decade, have built massive distributed systems around data storage and processing. They have a large user base, and they they needed to build these big tools and frameworks that would process large amounts of data and store them in various distributed data storage. And a lot of the networked systems that we see in plain sight today, not just internet, are examples of distributed systems. Any networked system is in itself a distributed system. The car itself is comprised of a lot of components that talk to each other. And these components in itself may fail, but as a system, they ensure that the car, for example, is reliable. And that's one point that I want to focus across this presentation, is that the system as a whole should be reliable, while still some of the components may be unreliable or fail. Similarly, the same goes with airplane. It has a dashboard, for example, for the pilot. And that dashboard consists of various components that work separately. A GPS tool, an engine tool, all of them carry out their own functionality. And for example, one of the engines is informed by the GPS meter on what amount of fuel is left and you need, and to inform other decisions. And the interaction of these components together make it a reliable and safe system. However, if one of these components fails, you need to provide an alternative solution. What does the engine do in case a GPS meter fails? Things like that. So you should be aware that a system is comprised of these components that may fail, and what do you do when they fail? How do you build fault tolerance around them? What are alternate solutions you provide in order for the system to carry out functioning? Traffic lights is another example. They are they can be, the traffic lights are a system that you can manipulate to address different traffic pain points. Train system is another one, train control systems. They help you make sure that no two trains go in the same track at the same time. Telephone networks are another system. Peer-to-peer systems are another example of peer-to-peer systems. Actually, the moment you start seeing these patterns, they are everywhere. Not just in internet or in software services. They are visible, these patterns or these systems are visible in a lot of other systems or daily usages. So why build a distributed system? There are many reasons, of course, but for most companies, when they go through different stages of growth, they start having a larger user base. They want to increase to provide scalability. They want their service to work for more users, for 1 million users, for 10 million users, for 100 million users, and so on. And one way to achieve scalability is to build a distributed system, because obviously with a centralized one, it is a challenge. Hand in hand with scalability, you have reliability. You want to be able to make a system more reliable, something that works for most users most of the time. And I know it's a little bit at odds with the definition of a distributed system, because by default, when you are distributing a system, you are dividing it into many other networked computers. And this means added complexity. You are adding complexity, and at the same time, you want to achieve more reliability. So I know that this looks at these two concepts look at odds with each other, but that's exactly what distributed systems try to achieve: reliability, but with added complexity compared to a centralized system. So the whole point is that you want to achieve this reliability with separate components, with components that build the system. And these components in itself may be unreliable, but the whole point is you need to understand how they can fail, understand failure modes, and build fault tolerance around them, such that you don't crash the whole system. It's an important concept to keep in mind. Of course, performance is also another very good reason why different companies build this, because you want to be able to serve them better with lower latency. You want your service to work in all parts of the globe. You want a user that accesses your service in Japan have the same user experience with low latency, with good response as a user in US. So you want your service most likely to be distributed or have caches of your data, of your resources closer to the user. And you achieve this by distributing the system. Availability is another very important concept, and what I mean by it is you have certain SLAs in place called service level agreements that say, I want to be able to offer a service to my users this many days a year. You define some of your SLAs on what your expectations are for a service. And then you try to live up to these expectations. You try to build a system that fulfills the promise of that SLA. One of them is uptime. You want your service to be up all the time. And if you know today you have examples of like users immediately notice, for example, when Facebook is down or Twitter is down. So they really focus on the availability. They want their service to be up all the time, as much as possible. And there are ways to express this in more technical terms. For example, the so-called 4 nines, 99.99% of the time. And that means 52.60 minutes a year, the system will be down. So you try to achieve or fulfill this requirement. There are also cost incentives. Sometimes, if you're a medium-sized company that doesn't have all the resources, engineering resources and other resources, you may choose to distribute part of your service or host part of your service with a provider. For example, with a cloud provider, you would rather use an AWS cluster to host some of your servers and services rather than build the whole infrastructure yourself. That would cost you more. So there are cost incentives as well into basically hosting this somewhere else. And the moment that you do this, the moment that you host part of your service somewhere else, you have made it a distributed system. So how to build a distributed system? As I mentioned, the most important part or concept to remember is that you are trying to build a scalable and reliable system, but you are using unreliable components. And you need to understand how these components can fail. What can go wrong? Understand how these computers might fail and how they can affect your service. The moment you identify these failure modes for computers, then you have to build fault tolerance around them. Basically, how will you handle them? And how will you ensure that the whole system will not fail? From experience, when you work with them, you see that a lot of things can go wrong. For example, the server that you're trying to reach is unavailable. What do you do then? Do you have a second server to serve requests? Most likely, yes, in a distributed system, because otherwise you will not be able to serve your customers. Or server may be up, but it's returning you a bad response. What do you do then? How do you handle corrupt data or bad responses? There are cases when the state or the data that you're holding for different users is lost. Have you made sure that you have a second copy somewhere else? Or do you use only one backing store to store all user data? Certainly, you most likely, and especially if you're a bigger company, you have thought of distributing this into more than one database. There might be security breaches in the servers. Their certificates may expire. How do you ensure that you're still talking to the correct server and it's not some man-in-the-middle entity? There are other things that can go wrong. And I know this from experience when building microservices that are hosted in the cloud. You may have memory leaks, and you may have different services that are hosted, let's say in Kubernetes, and they might use the resources of another service that is running on the same cluster with you. So what happens then? And of course, there are other things like natural disasters. A flood happens, or a police raid in a data center, or something similar. What do you do then? Do you have another data center elsewhere where in another availability zone where you have hosted your service? So a lot of these aspects make distributed system a systems discipline rather than just theory. Only when you start building them and through iteration, you see various aspects that can go wrong and how to build fault tolerance around them. I will try to just give an overview of 2 or 3 really important concepts in distributed systems that sort of guide your learning and understanding of them in general. The most important thing in distributed systems as a concept is time. If you run on a physical computer, on a local physical computer, it's very easy to establish what the time is. You have a physical clock on your computer and you can say, at this time, I did this action, or I saved this document, or I wrote, or I clicked this button. But when your computer, but when the computer is in a network, in a system with other computers, it's hard to agree what the global physical time is, because the physical clocks of different networked computers may not be in sync. And when different physical clocks of computers are not in sync, it's hard to agree, to decide global order of events. And I will try to illustrate, what does this global order of events mean? Why is it even important? Let's look at a few examples. Distributed locking is one. Distributed locking is used for all the computers that are in the network and are trying to use a shared resource. But who do you give the lock to in order to use the resource? You give the lock to the one that first asked for the lock. How do you ensure that a computer X asked for this lock before computer Y? You need to ensure the order of these events. You need to ensure that event for computer X happened before the event for computer Y. And even though computer X thinks that, hey, I asked for this lock at this time, which is earlier than the lock for computer X, these are physical clocks on these machines. But globally, can we agree that that was the time and that was the order? No, it's very hard to ensure this. The clocks in the physical computers may not be in sync. What you think the time is now may not be the same in another computer. And there are ways to alleviate this, but in general, it's hard to sync them. And most systems use NTP, Network Time Protocol, which tries to synchronize this time. And NTP may decide that your machine, for example, it has skewed, the clock has drifted too much forward, and it may try to roll it back. So that has repercussions for the establishing the order of events, for example. So that's one example. Here's another more practical example that makes more sense. A Twitter post. Let's say a celebrity like Dua Lipa posts something in Twitter and says, the first 10 replies to my post will get a free ticket to my concert. Now, how do you ensure that those 10 replies are the first 10 replies? How do you ensure that a person in Japan and a person in US, when they posted, that one is before the other or are at the same time? How do you ensure that those first 10 are really the first 10 globally? They may think that they were the first, but when you look at the system as a whole, is there an agreement on this time? Is there an agreement that this user in England was actually before this user in New York? You see why this order of events and time is important. The big companies, when they are building these services, they run into this all the time. The need for order of events in order to carry out the transaction, in order for their service to work. Here's another example. Stock exchange transactions. So stock traders exchange these stocks, and each transaction should be identified by a globally unique ID, so that Everybody participates in this network, and each transaction should be identified globally. How do you ensure that you can generate a globally unique identifier? If you are in one of the networked computers, how do you ensure that the ID that you generated is unique and bigger than any other ID that was generated by other computers? It is very difficult to ensure that. If you just use some random unique ID like timestamp in your computer, you say, oh, I'm going to use the timestamp. It's quite unique because it's just right now. What if someone used the same timestamp, or it might have a timestamp of the same time, but the clock of that other machine might have skewed forward, so the timestamp is bigger. Therefore, your timestamp will be backwards, will be older. So it's not very straightforward. It's difficult, and there are some other ways that you can think of. For example, in this case, what if these computers, instead of generating the global unique ID on their local machine, what if they talked to some other server and said, hey, give me your next unique ID, and I'll just use that. That's one way. But what if that server that hands out these IDs fails? Do you have a backup? So we're always going one step further on decentralizing, on distributing, and providing reliability when there's a failure. If you can see this pattern, it's always like that. You see what can go wrong, and then you ask how you can build fault tolerance around this particular component. There, in academic papers, you see various papers on also on virtual clocks and other options, but the whole point is basically that this is hard, and it's a main driver of research also in distributed systems, and it has ramifications and consequences in practice as well when you're building systems. Another one of the most important theorems in distributed systems, both when you study it as an academic topic, but also when you start developing and deploying these systems on the network, you will face or you will see this theorem in practice everywhere. It stands for consistency, availability, and partition tolerance. And what this means is that as we're talking about these components building a big system, they are communicating with each other. These components, these networked computers, talk to each other. They either talk to each other directly through some message passing like RPC, or through message queues indirectly or asynchronously, but they talk to each other. And what if they lose this connection? What if something goes wrong? And most certainly it will. You will eventually in your system suffer partition. It's called partition when the communication between these nodes or these networked computers fail. And what do you do when you suffer partition? You will most likely face the common trade-off that everybody faces when building these systems. You say, do I make it unavailable? I halt it until I reach consistency? Or do you still let it go, make it available, but at the cost of consistency? You might be running on old data, on data that is not, or on state that is not exactly accurate. So this CAP theorem formalizes limits on reliability. It helps you reason about trade-offs that you have to make if a system suffers partitions. And yes, the general concept is you either choose between availability or consistency when the system suffers from partitions. But I think that over time, and if you see, as you see in practice with many products that you probably use today, there are degrees. The trade-offs that you have to make are around degrees of availability and consistency. You don't have to say, I'll either choose availability or consistency. I think there are nuances to it, and I'll try to just, again, illustrate with an example. For example, this is the classic example you learn in Distributed Systems 101, basically. You have two ATMs in this case, and they talk to each other. They keep the state in sync. You can access your account both in ATM 1 and ATM 2. Probably in the real example, these two ATMs don't directly talk to each other. They have another server managing this connection, but for the sake of illustration, assume that these two talk to each other directly. And in theory, you should be able to carry out all the typical transactions in any of them. Deposit money, withdraw money, check balance, both in ATM 1 and in ATM 2. The only invariant that you have to keep is that, of course, you cannot go negative. Basically withdraw more than you have in your bank balance. So again, we're going back to what I've been reiterating throughout. What can go wrong with this system or with its building components? So ATM 1 may stop working. And in that case, it's pretty straightforward. You cannot withdraw or deposit or do anything with ATM. So you can go to ATM 2 in that case. There's another scenario where ATM 1 works, but not ATM 2 works. And then this situation is a little bit more complex. How do you deal with that? So let's look at one example. You have $100 in the ATM 1, and you go there and you want to withdraw some money. You withdraw $20, and now you have $80 left. So you put that $20 in your pocket and you leave. You're walking, and then you decide that, oh, I need to withdraw a little bit more because that wasn't enough. And on the way, you find ATM 2 somewhere. However, before you arrived there, there was a network issue between these two ATMs. They stopped communicating. What does this mean? This means that the system suffered a partition. These two ATMs cannot synchronize the state. And what does that mean? That means that when you withdrew $20 from ATM 1, and then partition happened, a network error happened between these two machines, ATM 2 still thinks that you have $100 because it didn't have the chance to synchronize on the state. It didn't have the chance to synchronize user data. So why is this problematic? It is problematic because when you go to the second ATM, what do? This is the trade-off that you will always face. We suffered a partition. What do you do now? Do you allow the user to deposit? Do you allow the user to withdraw? What are some of the actions that the user can do with ATM 2? If we go by the simple example of choose availability of consistency, that would translate as this. You can either keep carrying out these transactions as if nothing happened. You can deposit, withdraw, check balance, but with the wrong state. And then you run into the risk of maybe even going negative because you think you have $100 and you try to withdraw $100. Or you can say, sorry, I can't work. I need to wait for the network to heal to make to come to a consistency with ATM 1, and then I will let you carry out these transactions. So you can see that in both cases, if we choose availability, we might run into risk of going negative because you don't know what the bank balance, the exact bank balance is, or you can choose consistency, which means you can wait until network heals and then you know the correct balance. However, what does that mean? You have made it unavailable for the user. The user has to wait, or maybe try to go to another ATM. So that's the trade-off. These are the trade-offs that the CAP theorem talks about or tries to provide some bounds and limits on these trade-offs. However, you can choose the degrees. This is what I mean by the second point, degrees of availability and consistency. you may allow the user to deposit money, even if there's a network partition, or you may allow the user to withdraw only $10 in 5 minutes. And in this way, you make the system a little bit more available, not fully unavailable, but you provide some functionality. And at the same time, you don't run into the risk of the user perhaps going negative in the bank balance until the network heals. So the boundaries are not very rigid. So now we are considering various degrees of availability and complexity and consistency in your system. So these are always trade-offs that you make, and depending on the service, you will iterate on your solution over time. Yeah, so the network heals, and now you have the same bank balance in both ATMs. And another important concept that you will hear whenever you go and read anything on distributed systems is consensus. And consensus protocols are supposed to, they are used to achieve agreement between computers. So what do I mean by that? Why is it important that computers agree on anything? What are they agreeing on? So just to illustrate, you have a store. That's your service. You are offering different items, be it clothes or games or whatever. And you are selling your products everywhere. You're not selling it only in US, you're selling it in Australia as well, and China. So how do you make sure? So these different users are going to the store, most likely through a website or a mobile app, and are checking at the items there. You have this many items of this category, this many items of this category, they are in stock, they can buy these products, and so on. So how do you ensure that any user in Australia and a user in Iceland, when they hit your service, when they request your service, how do you ensure that they see the same thing, that they see the same store? Because while they were browsing your store, someone else in India bought some items. Are they going to see 10 items or perhaps 8 because this user in India bought 2? So we are talking about, this is the value that different computers need to agree on in order to reflect a state that is common for all users. What do I mean by that? So this store is most likely not stored or provided or hosted in just one server. It is most likely replicated across many different computers in the network. So how do you ensure that the store that was hosted in one of the computers that served a user in US is synchronized with the other replica that is maybe serving requests from Japan? So that's the real challenge in distributed systems. You have your store, which is a service replicated across many computers, and different users around the globe are accessing the same service, but probably they are they receive the different replicas in your network, receive those requests and answer to those requests. However, all these network computers need to talk to each other to agree on this value all the time. This is something that happens all the time. In this case is to agree on that these are the items sold and not sold in your store. But we're talking about a generic concept here, which is they need to agree on this value all the time. Computers in your system, they will be talking all the time with each other and syncing on their state. This is why it's important. And one of these replicas that is maybe serving requests for a certain region may fail or may lose the data. What happens then? can the users of that region, let's say Europe, still keep browsing and shopping for items? Certainly they should be able to, because you have thought of this failure mode and you have replicated or provided redundancy for this server and for this region to some more replicas. So that's the whole idea of this. You iterate, you find where certain computers can fail, how they can fail, and how do you handle them. And generally consensus protocols, the one that I will mention next, deal with fail-stop failures. So computers just stop working. They just stop working, or they have a network failure. We're not talking about Byzantine failures where computers are malignant. Basically, they want to harm the system. They are actively working to harm the system. In this case, we're just talking about just computers failing for various reasons. And the most known one is Paxos. Paxos is known in academia. The paper was written by Leslie Lamport, and it was known for it being a little bit complex to understand and to implement. So there's another version called Raft right now, which is supposed to be a little bit simpler. But the overall point of Paxos is that it provides some bounds for you to reason about, again, how to achieve consensus or how to achieve agreement among computers. And 2-3 important points about it are, how can you recover from failures quickly? Can you recover from failures quickly? And the answer is instantly. And what do I mean by instantly in this case? Is that if one of those replicas in that store failed, should you keep browsing? Should you be able to keep browsing and buying items? The answer is yes. And if you use a consensus protocol, this is something that you will consider, and you will think in your design and in your implementation. Basically, you should have a backup. You should have another server that will be able to continue serving you. How many servers do you need in order to run a consensus protocol like Paxos in your system? And you need 2 machines plus 1, so you need at least 3, because it takes into account how many machines can fail while you still are able to ensure a reliable and functioning system. And of course, if you have more servers in your system, it's not the same when you have 5 and when you have 10 computers in your system, each doing their own task. Because if you have 5 and they all need to agree on a certain value, then they need to exchange messages among each other. And the number of messages will be relatively low in that case. But if you add 10 computers, now they need to agree on the new value. We're talking about a lot more messages. And as I point out in this 3rd line here, how many messages need to be sent to achieve consensus, is the growth is linear with the number of computers. The more computers you add, then you have more messages that are exchanged among each other to achieve consensus, and the growth is linear. So I won't go into details of this because it's a topic in itself. It's just I want to illustrate why it's important and how it is used in distributed systems. And I would like to conclude the talk here. I didn't even provide a conclusion slide because I think that the domain is really big and it's hard to conclude. But I want to say that as a discipline, it's a systems discipline. It's something that cannot be studied just in theory. They help. In most cases, it's something that you need to experiment with. You start building a small solution and you iterate on them. And you constantly find or identify parts of the system that are not reliable, understand their failures, and build fault tolerance around them. I would say this is the most important takeaway point from all of this. Thanks. I can talk to you more also in private, but if you have any questions right now, please feel free to ask.
Thank you, Flutra, for the presentation. It was very detailed and interesting. So I will start with the first questions, and hope that also the other participants will have like a question. If you don't want to speak, or you can write in our chat, so and Flutra can answer. So feel free to write there. So the first, so most of the questions, so I had you nullify them because you made questions and then responded to them. So it was very nice. So a general question. So it is, for example,
I guess.
Okay, do you hear me now?
Yeah.
Okay, so what I was saying, like a general question, it is that for you as a software engineer, and for example, you are going to design like a large scale distributed system. What is one thing that you keep in mind? So you don't know if you are going to design this this distributed system for, I don't know, for Netflix, or you are going to create it like for example, like Bitcoin cryptocurrency, or it doesn't. So it's not very well defined, this part. So what is one thing that you as a software engineer you always should keep in mind when you approach this the design of a system?
As I said, first you start smaller. You don't build a system initially saying that I'm going to serve 1 million users. You may try to define some bounds, or as we call it, do some capacity planning and say, in general, we expect this many users a second, and they are going to hit our website or click this button this many times a second. And based on that, you take that figure and you say, how can I do some capacity planning for this? What would I need? I would need, will one server be enough? Can they handle it? What is a correct a metric? Is 100 seconds, 100 requests per second okay? Can my server handle it? And if not, can I increase the number of servers to serve if I get more users? At the same time, if you're storing some of the user data, you say, how much am I storing? Am I storing their first name, last name, other information? How big is this record? And if I also have to encrypt this, encryption adds some size to the payload. How much more do I need to just store this data and then access this data? Actually, often in practice, what you do is really you start smaller, and then you just put some metrics that are called KPIs. You say, I want to see how long it takes just to load this record from the database. I want to measure this latency. How long does it take just to write it? Because all of those take time when you serve the user. And then you build some basic dashboard saying, I've been receiving 100 requests per second, users doing this, and every time we needed to load their data from this database, it took us this many seconds. So maybe that's why it's taking longer to serve them. What if we scale this better, or if we sharded our database differently? Can we reduce the latency? Can we reduce the time it takes for the response to go back to the user? So often it's a lot of the incremental things that you put in place, and you just start measuring early on. You measure everything early on. Like, it seems like these 2 servers are not enough. We have a queue, let's say, of tasks, and this queue is not draining enough because we can see that those tasks are not being picked up from the queue to be processed. What if we added another server? Let's see what happens to this queue. Oh, now it's processing faster. So with the early solutions, you also put metrics or KPIs that help you say, it seems like this part of the system is not really fine-tuned well. And they give you a more educated guess on what to do next. So, yeah.
Okay, thank you for your answer. Are there any questions that you have for for Flutra. Also questions regarding her professional career or also regarding related to her experience in Netflix, or so she's currently working in Silicon Valley for a company. So maybe you are interested to know something related to her work or how she manages her daily tasks. Okay, I'm answering you. So how it is working for a large company in Silicon Valley or working for Netflix, or compared to your, for example, your first experience with, I don't know, have you worked in Kosovo or here in Albania?
No, because I left. I left after high school. I want to probably just say 2-3 words in general, since this is targeting girls and trying to encourage them to go into the computer science domain. It's and I'm saying this from a personal experience. It largely is a lot of our barriers are psychological. They are not really, they don't exist in practice. A lot of them are because we put a lot of blockers or barriers in front. We face different dilemmas and fears that, and I would say this largely affects women, not just in our region, but more widely. But I want to mention something, especially in Eastern Europe. The way we grew up with the education system is that it is largely plagued by the fixed mindset. And what I mean by that is that you are told early on that you are good in math or you're not. This is the person that is good in math, and this is the person that is not good in math. And then you embed this thinking, this mentality early on, and you convince yourself that you're either good in math or you're not. And it's a mentality that keeps you backwards, in the sense that it doesn't allow some flexibility for you to improve. Basically, with this thinking, you don't give yourself the benefit of the doubt. You don't give yourself the flexibility and space to improve, because you think that you're not good at math and you can't improve. And I encourage girls to embrace a growth mindset, a mindset where you may not be good right now at a certain topic, but you will get better if you work on it. There certainly you can assess yourself that you're not good in something, but that doesn't mean you will not get better. It's a small difference, but it's a small detail, but it makes a huge difference. And I can guarantee you from personal experience that if you try to transition from fixed mindset to a growth mindset, you will do wonders just by switching to that mindset, because it will give you some personal space and motivation to and belief that you will improve, whether it's in computer science or in mathematics and so on. There's no such thing as you are good at something and you're not good at something. Yes, there are certain people that are more advantaged because they either went to a better school or had better resources. But today, with all these resources online, you have the opportunity to improve constantly. If you are getting bored with something for 2-3 weeks in a row, stop. Find something else to learn. Read another article. Try something else. Another programming language, a small program that does something. And little by little, you will improve. By just transitioning, again, from fixed to growth mindset, nothing can stop you.
Okay, thank you for your message. Okay, I believe there are any questions, other questions related to the distributed?
I will share with you my personal email, so feel free to ask questions or anything in particular, or perhaps how we can organize something more concrete later once we're done with the pandemic. but I'm sure that in the future we'll be able to collaborate more and perhaps even think of other ways, other modalities of organizing some workshops or sessions. And in the meantime, yeah, I'll leave the email with Arisa and she can exchange it with you.
Thank you.
Some messages right here.
Writing in the chat, so.
Yeah. Yes, of course. There are always pressures. There's politics because the human nature is such that I don't think it's very specific to a company. It's human nature. Often when you are in bigger teams and you need to prove that you are doing your work, that you need to prove that you are moving the whole team forward there, and then you need to prove that your team is indispensable compared to other teams' work. Then all these dynamics come into play of like and politics. I think this is I wouldn't even say this is particular to a given company. This is in general, and especially if you're a woman in engineering, there are other of course challenges, but as I mentioned, a lot of challenges sometimes come from you, your psychological barriers that you put in place. And if you lift them, you will be able to do better. And I know that the girls are disadvantaged. Yes, there are various sometimes not just visible but invisible like forms of discrimination. But if you embrace the growth mentality, you will be able to handle them with more resilience. Just as we're talking about a distributed system, you will be able, even if you know that there are actors in your workplace or in your environment that are either not encouraging you, not supporting you, or actually even working to harm you, you know that you can handle them because you have built some resilience within you. So that's all I can say. It's a long path, so don't see it as just one thing and a particular bad boss or a bad colleague didn't inspire me here, therefore I couldn't move on with my work. Just look at the trajectory, whether it's a professional trajectory or a life trajectory, something that is long. And it's just not one point, it's a lot of points. So look ahead.
Thank you. Po pyes në Shqipa tashmë, ka në pyetje të tjera? Besoj se ja. Kështu që, okay. Faleminderit.
Yeah, mos nguroni, mund të më shkruani nëse keni ndonjë pyetje dhe po them shpresoj se në të ardhmen e afërt edhe mund të shihemi dikon në Tiranë e të organizojmë edhe aktivitete tjera.
Shpresojmë dhe shumë faleminderit që u bashkove sot dhe që gjithmonë je e gatshme edhe për të na mbështetur e për ta ndihmuar, edhe për motivimin, sepse speaking që bëre pak më parë është shumë i rëndësishëm dhe shumë faleminderit.
Ju tregoj që është pjesa gjysma e detyrë, gjysma e punës. Është një qasja pak më pragmatike.
Okej, faleminderit për sot. Atëherë një njoftim të vogël para se ta mbyllim ditën e sotme. Eventi i radhës do të jetë në datën 20 korrik dhe do të jetë e ftuar Erisa Karafili, e cila do të flasë për cyber security, kështu që mund të bashkoheni edhe në eventin e radhës. Shumë faleminderit Flutura për bashkëpunimin e sotëm dhe për speaking. Ndërkohë personat të cilat duan ta ndjekin në veçanti pjesën e technical talk, që ishte shumë e rëndësishme e shpjeguar me detaje, do të postohet së shpejti në Women Take Makers YouTube. Aty mund të gjeni gjithë informacionin. Kështu që faleminderit për sot, një mbrëmje të mbartë. Faleminderit Flutura. Mirupafshim.
Gjithë mirat. Mirupafshim.